Swayam Prabha. Digital India. Educated India.
Today, we'll resume our old session and conclude. We started talking about formal syntax, how syntax was made formal by Noam Chomsky in 1950s and 60s, and we also saw the generation of a grammatical string and the blockage of an ungrammatical string. Today, we will try to generate a few more strings by using the rules yesterday we saw. Unfortunately, all the rules are not on one page, but we shall try to generate another string. Now, we can concentrate on say, we'll make a sentence like the man hit the ball. We can see that this is the past formation, right? This is the past tense of hit. How we can generate this sentence by using our grammar. We go back and now we show the generation. So we know that the first step would be like this: sentence goes to NP VP. This is another way we can derive a tree. Instead of writing sentence and then writing NP plus VP, we can directly show the branches. That this shows, actually this can be translated as sentence and then NP plus VP. So we are going to use this format today. We are going to use the tree format today, not the rewriting format. We can understand that they correspond to each other, but this is easy to see and to read. After that, and remember that we are going to make this sentence: the man hit the ball. We shall see how we can make it. Once again, it's a singular noun. So this rule I need, that is NP goes either to NP singular or to NP plural. Our NP goes to NP singular, and the VP goes to verb plus NP. Now remember that if we wanted to write, so this step would look like NP sing plus verb plus NP in the old format, which is not something we are following this time. But we can see the equivalent derivation in this format, in the tree format also. Once again, NP can go to NP singular, verb goes to aux plus V. So as usual, aux plus V, and this NP now goes to three things: T, N. Because it is singular, it is now. We are following this rule, rule number 4. Here the same thing happens. It goes to three things: T, N, and nothing. Now we shall see the Aux rule. In this case, what we have to do is, we have chosen just one thing. So here aux goes to C. We haven't taken the have formation or the being formation, we just have taken the C formation. So then what will happen? We get back to it. Aux goes to C, which is perfectly allowed. And what will happen to C? we remember that in the context NP singular, C gives S, and in the context, and when I want to use past, I don't need any context, it is just past, and I want the past formation, so I can rewrite C as past, and there is no option but rewriting T as the, and I want N to be once again man, and nothing is nothing, and V I choose hit, T goes to the, N goes to ball, nothing is nothing. Now there is a morphonemic rule we shall see, which tells us that past plus het is actually het. Now remember, this is a word, an abstract thing, but this is a physical thing made up of speech sounds, real speech sounds like H and I and T. So it is actually het. So with that, so now we know how this goes to this sound. So the sentence becomes, so the word becomes this becomes this, and this is het, and once again this becomes this, and ball it looks something like this. So with all that, we shall see how it looks like in the rule. So this is a string that actually can be pronounced by a human or a machine. So this is an alternative derivation of a sentence, and also we can derive a sentence like the man has hit the ball. We'll try this also. We can try it here, we need not, now we almost know the rules by heart. So here once again sentence, which is our base step, sigma, and sentence goes to NP, VP, and in this case also the NP is a singular NP, NP sing, and VP goes to, I think, verb plus NP, and verb goes to aux and V, and NP once again goes to, because we want the ball, NP singular, and then this goes to three things, T, N, and nothing. This also goes to three things, T and N and nothing. And in this case, we see that this rule, we are choosing two different things. We are taking C as well as have N. That makes it C have N, and V goes to het. V goes to het. So there we are, and T has to become the, this is man, and here it is the, and ball. Now we are pretty close. C in this case has become S, because look at the context, it is NP sing, so C becomes S, and have N is haven. Now the point is, we have and S, they will combine, and we have N plus het, they will combine. Now we shall see what happens. We can see that when S and have unite, we have has. So we just rewrite here, we just rewrite this S plus have will make has, and also we see that het plus N remains het. So N plus het will be nothing but het. So already these two have been realized, they have been sort of manifested by using the rules, and the once again becomes something like this: man is this, and has hit the once again, and ball looks like this. So we find once again the final string, which is absolutely grammatical. So the point is, if a string can be made by following the rules, then we call it grammatical, and no ungrammatical string should not be made, should not be generated by the rules given. That's the most important point. We can see that all these strings, all these sentences, we call these sentences, can be made by following the rules Chomsky has given us. So that is a test of his grammaticality, and we can see how this formal system is also, it's very complete in the sense, complete not in the sense that it can generate all grammatical sentences, but you can see that it's a list of finite things, and it's very compact. That is what I meant by complete, not really complete. It's very compact. You can see that all the rules are given. You can also see how all the rules work and how finally you come up with something. So here is the tree for the first sentence: the man hits the ball, and so the last strings are not there. We can just write those things. So actually this is given by Chomsky himself in his syntactic structures, but we can, as I have shown, derive it either way. We can either use the phrase structure rules and the rewriting rules, that is, we can physically rewrite sentence. So the next step could be NP plus VP, or, and then this step would look like NP thing plus verb plus NP. So either we could do it this way, or we can derive it by using the tree structure. Both are fine and they're equivalent. So we don't have any problem as far as this duality is concerned, this double derivation is concerned. Basically they're equivalent derivations. So then we shall go to the next segment, that is propositional logic. So after having studied formal syntax, we now need to understand formal logic. Logic in the Western world started with the works of Aristotle, and in that sense, from the very beginning, logic has been formal. Formal because I'm not saying it was Aristotelian logic was formal in the modern sense of the term formal, but still it had formal elements. Logic, at least Aristotelian logic, always had science and some kind of science for combining science and then constructing bigger structures, more and more complex structures. But formal logic, the way we know it, is not very old. So logic in this form, formal logic in this form rather, is pioneered by Frege, and the ideas actually were, the ideas originally were Frege's, and then Russell, Whitehead, and many other logicians contributed to the field, and we see, and the present notation actually is in a sense adopted from Russell, not that it is exactly the Russellian notation. This notation, the notation we are going to use, is used by Montague and Kalish in their text, and because we are doing Montague semantics, we want some kind of compatibility, so we are using these notations. before you start talking about logic or logical systems, we need to understand what we mean by a proposition. The unit of logic is a proposition. What does anybody mean by the word proposition? We know that a declarative sentence must have a truth value, or most of them have truth values. For example, with the moment you say that Ram hits the ball, it is either true or false. In most of the cases, either Ram hits the ball or not. But this sentence is not the proposition, although the proposition is represented by this sentence. Roughly speaking, a proposition is the logical form that underlies a declarative sentence. Consider the following sentences. Ram says that I am useless. Then Tom, about Ram, says to John that he is useless. This he here is Ram. And then John says to Ram that you are useless. All these are actually different sentences. But why are the different sentences? Because they are made up of different sounds. The grammatical structure is not exactly the same. In the first sentence, you find a pronoun, and also you could have a noun. Somebody else could have said Ram is useless. And so they're all different sentences, and a grammarian would be interested in the structures and the structural differences of these sentences. But we can easily see that one logical form underlies in all these three sentences. Ram's saying I'm useless, and somebody's saying that he is useless about Ram, and somebody's saying to Ram that you are useless. So that thing is a proposition. A proposition is either an assertion or a denial. And as I already said, a sentence is the concern for a grammarian, whereas the proposition is the main concern for a logician. So the logician would completely ignore the differences between the sentences we already mentioned, like he is useless, or Ram is useless, or I am useless, or you are useless. For the logician, the most important structure is there is a set or a function. So let us first talk about sets. There is a set of individuals or things that are useless, and Ram, an individual, a specific individual, belongs to that set. So we first distinguish between a sentence, a declarative sentence, and the proposition that actually underlies the sentence. And then we go to prepositional calculus. Now, prepositional calculus is the very starting point of formal logic. This is not the only calculus in logic. There are several calculi, but prepositional calculus is the very is the very core of the entire thing. You update it with additional rules and additional signs, additional operators, you get the predicate calculus. You update that a little more, you get the modal calculus, and you keep updating the system, you get different things that can do also different jobs, and they belong to different complexities. Propositional calculus actually is about mainly things that that connect sentences or propositions like and, or, if then, it is not the case that, and things like these. So we start studying a very simple logical system. It is actually prepositional calculus, and then after a few sessions we will study predicate calculus. So the system has mainly variables, prepositional variables. They are P, Q, R, etc. It has logical constants. Logical constants or logical operators are of two types, monadic and dyadic. A monadic operator operates on one single preposition, and a dyadic operator operates on two prepositions. So the monadic operator we can easily see is this, and I have mentioned 4 dyadic operators here. Not that all 4 are important, because one could derive from others, but still for the sake of convenience we have 4 here. So we have and or. This is if then informally speaking, and this means if and only if. Now the point I would like to make here at this point is, we need not interpret these symbols here. So the first thing is, so the system can survive without being interpreted. We have interpreted in the very beginning, but we could just state the operators and how they form composite sentences out of atomic sentences. We could have just seen that, but anyways, already we have given some interpretation for the sake of, once again, kind of semantic convenience, so that we need to have some idea about what these things could be. So, and we need punctuations. So we have brackets of all different types, mainly 3. We could have more, we could manage with 1, but once again for convenience we have 3 different brackets. So the system looks like this. Once again, like any formal system, we require rules for this. So the first rule, R1, is a prepositional variable is a WFF. WFF meaning well-formed formula. So once again, we understand that our prepositional variables are P or Q or R and stuff like that. So each one is a WFF, and we can see that this is our step 0. Every formal system must have a step 0. We can remember the Smulyan system which we discussed in the very beginning. It had 4 elements at this level. It had A, B, AB, and BA, and nothing else. The Chomsky system in syntactic structures had sentence, which would be rewritten into NPVP and stuff like that. Now in this system we have P, Q, R, etc. These are absolutely atomic, and we are not going to split these things. We treat them as units of our system. Now the first formation rule, where the monadic operator operates, we say if alpha is a WFF, then so is neg alpha. We'll call this neg, which stands for negation. But once again, the interpretation is not important right now. Then the second formation rule, rule 3, is if both alpha and beta are WFFs, then so are alpha or beta. That is the first one. Alpha and beta, if alpha then beta. We need not read them in the interpreted form. We can just say alpha and this sign beta, whatever this sign is, alpha, this sign beta. So we could have easily do that, because our job now at this level is not to interpret anything. We are just stating rules for forming different prepositions in our system, different molecular prepositions. The atomic prepositions are given, they are P, Q, R, etc. Now the interpretation part. Now we enter the semantics of it. Neg alpha may be interpreted as it is not the case that alpha. So we can say it is not the case that Ram hits the ball, which denies some kind of an assertion. So what does it do? It changes the truth value of the declarative sentence or of the preposition it takes. Now the next is alpha or beta, that is this, and then alpha and beta, and if alpha then beta. These are all WFFs. And after this there is no other rule that would create WFFs. So this is in short the system. And finally alpha if and only if beta. One very important thing, we should not confuse the rewriting sign right arrow and if then right arrow. Although they're the same symbol, they mean different things, and we need to understand this contextually. For example, when we write S goes to NPVP, we understand that it is not that S implies. So we can say that when we write alpha implies beta, we can say that it is to be interpreted as if alpha then beta. So in short we call it implication. We say that alpha implies beta. So we need to interpret this thing contextually. Now after having done this, we will see the construction rules or the construction of different prepositions, different composite molecular prepositions in this system. So suppose we need to see whether a construction is good or not. Let us consider for example something like alpha. Is it a grammatical string? It is something our system can produce or not. We can easily see it is not. It is because yes, had this been this part, that is or alpha, had or alpha been a WFF, we could have derived the entire thing, but there is no rule that somehow allows me to derive or alpha. Had there been a beta, I could have said, now this is fine, this is fine, but this is not fine, because I cannot derive it in the first place. I cannot derive this string, so this is a bad string. And so there are many such bad strings and good strings. So for example, I cannot come up with a string like neg alpha neg, because once again, had alpha neg been, had it been a good derivation, we could derive neg alpha neg. But because this is a bad derivation, it is not possible for us to derive this part, we cannot derive the whole. But on the other hand, we can derive several things. We can easily see that alpha implies alpha or beta implies alpha is a WFF. Now another very important point, we distinguish between PQR on the one hand and alpha, beta, gamma, all the Greek letters on the other hand. The Greek letters are metalogical variables, whereas P, Q, R, etc. are logical variables. What I mean to say is, when I write a rule, I write about logic, I I do not. So there is a difference. We need to do it. I just introduce it now. Anyway, we'll have to talk about it in details when we talk about the semantic systems. But I just introduce that that discourse here. So the point is this: when I write P implies Q, I come up with something that belongs to my logical system, because P is a prepositional variable of my system. But when I write that if alpha is a WFF, then so is neg alpha, this alpha does not stand for a particular variable, logical variable P or Q or R or anything. It stands for any WFF that is produced or that could be produced. Now, also at the same time, rules are metalogical, because so we distinguish between an object language and a meta language. What we mean by these two? Now, I can talk about French in English or about Sanskrit in English. Now, when I talk about, so suppose I'm talking about Sanskrit in English, I may say that when my subject is Ramaha or Ghataha or whatever, Pataha, anything, my verb can be one of these: bhavati, or tishtati, or drushyate, or anything. Now, I can say when my subject is Ramau, Ghatau, Patau, my verbs would be one of Bhavataha, Tishtataha, and stuff like that. Now, I now give rules. These rules I give in English, right? These rules are not part of my object language, Sanskrit. I'm talking about Sanskrit. So, so there are two different things. I talk about Sanskrit and I make Sanskrit sentences. Because my destination language is Sanskrit, I call it my object language. So any Sanskrit sentence is my object sentence. But these sentences in English, sentences that talk about rules for producing Sanskrit sentences, are not in Sanskrit. They are in the meta language in this case, which is English. And we must not confuse these two things. Yes, it could both be English. We could talk about English by using the meta language English, but it need not be the case all the time. So when we write a rule, we do our activity belongs to a higher level. We make comments on what we are going to do. So for example, when we say that if alpha is a WFF, then neg alpha is also a WFF. When we say this, we make a comment on infinite WFFs of our object language that will have. So, and a WFF can be P, or it can be P or Q, or it can be P and Q. It can be P and Q implies R. It can be anything. So this applies to all. If anyone is a WFF, then so is the negation of that. So each one is a WFF. So this is what is meant by meta-linguistic variable. So alpha is not an object linguistic variable. Alpha is not part of my logic, but it is part of my language through which I write rules about logic. So that's the reason we have this difference. We need to see this several times. This is going to be a very important difference or very important theoretical thing. in any semantic system. We need to distinguish between variables of different types. Anyways, now after having seen this, we can very easily see that this, that is neg P and Q implies R, is a WFF. How can we justify this? We use rules. The first thing is to make something like Q implies R. So we know that Q is a WFF. We also know that all these standalone signs are WFFs. These are prepositional variables. So we have, so Q is a WFF, R is a WFF. Then we apply rule 3, which says that if both alpha and beta, remember alpha can stand for any WFF in logic. So if both alpha and beta are WFFs, then so are alpha or beta, alpha and beta, and alpha implies beta. So we apply this rule 3 and we say that because Q and R are WFFs, by using rule 3 we produce Q implies R. We establish Q implies R as a WFF. Then at the next level we also know that P, the standalone letter P, is a WFF. Once again we use rule 3, which says that if alpha is a WFF and beta is a WFF, then so is alpha and beta. Now, so let alpha stands for P and beta stand for Q implies R. And then finally we form P and Q implies R. So we can see that this is a WFF. And then we apply rule 2, which says that if alpha is a WFF, then neg alpha is a WFF. So already rule 3 establishes this as a WFF in the second step. In the third step we can say that because this is a WFF, this too is also a WFF. So this, so these steps establish neg P and Q implies R as a well formed formula or a WFF. So we can easily see that although this is a WFF, P and Q is not, because there is nothing, there is no rule that allows me to have two occurrences of and. It can have, it can be only once. So it cannot be there twice successively. So we can see that already syntax has started working. Syntax in the sense here, syntax means in general the science of producing legitimate or grammatical strings. So it must, any syntactic rules must distinguish between grammatical constructions and ungrammatical constructions. We can see that this is ungrammatical and we cannot make it, and this is grammatical and we can make it as desired. So we write grammars because we want to come up with only grammatical constructions and we want to block all ungrammatical constructions. And we can see that these three very simple rules here can actually produce infinite sentences, infinite number of sentences in prepositional calculus, and it can also block infinite number of wrong sentences, wrong grammatical, wrong constructions. Now after having done this, we need to see some deduction rules, how to apply these rules and stuff like that. We need this because we'll see a lot of constructions, we'll see a lot of implication rules in formal semantics. So we need to introduce those things. So we see the rules and we try to understand these rules intuitively first, and then when time comes we'll see this from a technical perspective. We have seen the rules of generating prepositions in this logic. So in the next step we'll see how these rules rules have worked. Now this is a set of different rules. These are deduction rules, which means that through these rules, two or more prepositions would imply, or even one preposition, one or more prepositions would imply other prepositions. Let us start with the first rule. So this is a very simple, very simple set of rules. These are not at all complicated, but these will help us see how deduction works in logic. What I mean by deduction is the art of concluding one thing from another. Now, for example, if somebody tells me that it is not the case that Ram hits the ball, what do they actually mean? They practically mean that Ram hits the ball. The two different negs, it is not the case that, cancel each other, and we are left with Ram hits the ball. So that intuitive thing is expressed through this. This says that neg P is equivalent to P. What is equivalence? Equivalence is a two-way traffic. It means that if I have P, from that any time I can conclude neg P, and if I have neg P, then at any time I can conclude P. So this is the first rule. Not that every rule is an equivalence rule. Equivalence rules are very handy things because they can be used anywhere, but one-way rules are slightly trickier. We'll see that. So the next rule, so there is a name for this rule. Technically it is called double negation. We'll just write DN, that will do. The next rule is called conjunction. This is not an equivalence rule. This dot works as a divider. This tells us that, well, this is the limit of one sentence, then another sentence starts. We actually will use the word sentence in an informal way. We will mean, normally we will, what we intend to say is a proposition, but we'll say sometimes it's a sentence. So it's more of a habit than the correct way of doing it. But we have this habit of calling prepositions sentences, and sometimes we'll do it. Now, the next one says that if we have both P and Q, from that we can conclude P and Q. So it is something like this. If I know that if it is true that Ram hits the ball, and also if it is true that John hits the ball, from that I can conclude that Ram hits the ball and John hits the ball. This and was not there in the premises. These are called the premises. So it was, this and was not there in the premises. We introduce and in the conclusion, but this is a new string, and this is like we license a new string on the basis of other things given. So, and this is actually implication. These are all implication rules. These two together imply the third. P and Q separately imply P and Q. So this is the second rule, which is called conjunction. We'll just write conj. That's the short form. And then we go to the next rule, which says that. So rule number 2, that is conj rule or conjunction, is actually an introduction rule. It brings a new element, a new logical constant, namely and, which was not there. Rule number 3, which is called simplification, is an elimination rule. What do I mean by that? It was there. There was a logical constant, there was a logical operator in my premises or in my premise, and then I eliminate it and I just get rid of it and I do something else. So what I do is I know that P and Q. From that I can easily conclude P. So this rule is called simplification. Simply we can write SIMP. So it is something like saying if it is true that Ram hits the ball and John hits the ball, then we can comfortably, easily say that therefore Ram hits the ball. We can single out one conjunct. There are two. We can just single out one conjunct and assert it. So the fourth rule is addition, which is once again an introduction rule. In the premise there was no or, but I introduced it in the conclusion. How does the rule work? It works in this way. I know P. From that I can anytime say P or Q. So if I know that Ram hits the ball, without any hesitation, anytime I can say that either Ram hits the ball or 4 is a prime number. Now, although 4 is a prime number is not true, it doesn't matter. If Ram hits the ball is a true sentence, then either Ram hits the ball or 4 is a prime number must be true. It is because this thing, or, it claims, it asserts that at least one is true, and that at least one is true because P is true. Because P is true, I can safely conclude P or Q must be true. So the truth value of this sentence, P or Q, will never depend on the truth value of the other thing, that is Q. Whatever it may be true, it may be false, P or Q must be true just because P is true. So this rule is called addition. This is the or introduction rule. And the next rule is the or elimination rule. It has a fancy Latin name, modus tollens opponens, or MTP, that's the short form of it. So the rule says that if it is given that P or Q, that means if P or Q is true, I can somehow derive Q from it, provided also I get to know that nec P is the case. Intuitively speaking, P or Q asserts that either P must be true or Q must be true. And then nec P says, but how do I know which one is true? Either P is true, at least one of them is true. I have no guarantee. There is no guarantee that P is true or Q is true. But the next one kind of guarantees that Q is true, because it says that nec P is true or P is not true. Now, if one of them is true and if P is not true, then Q must be true, and this is called modus tollens opponens. This is how I eliminate the or that was there in it. But this elimination is difficult and elimination is very easy. So for example, what is and elimination? Simplification. If I had P and Q, very easily without anything else, I could just say P, or I could also just say Q. But here it's not that easy. We need another premise here, that is nec P or nec Q. If we had P or Q and nec Q, similarly we could somehow conclude P here. So this says that at least P, either P or Q is true and Q is not true, therefore P must be true. So this is called modus tollens opponens. And we then go to the if then elimination rule. I just need to get rid of some of it so that we can work on this page. So here we'll see how we can get rid of if then. So there are two such rules. One is called modus ponens, the other one is called modus tollens. We first concentrate on modus ponens. So it is given that P implies Q. How do I conclude Q from that? I can't, because P implies Q roughly means that if P is the case, then Q is the case. But how do I know which one is the case? I have no evidence. Now if somebody says P, then I have evidence. I have evidence in the sense, if somebody says P, then I have a ground for concluding Q. It is something like this. So suppose it is true. I'm not saying that it is true, just suppose, assume it is true that if it rains, the soil gets wet. And then somebody comes and tells you it is raining. What is your conclusion? Then the soil must be wet. So this is a natural deduction rule. It is because it is something like P implies Q. If it rains, the soil gets wet, and then it is raining, so the soil is getting wet, or the soil is wet simply. So this rule is called modus ponens. We have got rid of implication here in this rule. There is another way of doing it. We could also get rid of the implication in some other way, that is this. So somebody once again has said that, or we know it is established, say that if it rains, the soil gets wet, and somebody comes and tells me that it is not, the soil is not wet, which definitely means, which definitely implies that then therefore it is not raining, because if it rained, the soil would definitely get wet. Because the soil is not wet, we conclude that it is not raining. This is called modus tollens. So this actually, here we eliminate this thing implies or if then on the basis of a neg. So without that neg we couldn't have done it. So the elimination, there are two different elimination rules for this. So this is roughly what we can have in the deduction, in the set of deduction rules, and we can I just showed some small deductions in this system. Now we go to a very important section. Can all these things help us understand the natural language, or can they not help? Definitely they can help us understand the natural language. It is this way. So the next section is on logic syntax interface. This is an informal study. We are not making it absolutely formal, but it will have the formal structure. Just need to make space and erase a bit of it. And yes, so here we need to add a few more rules to the syntactic rules, and then not that these rules are added by Chomsky in syntactic structures. I just added these rules for the sake of convenience, so that we can do a little bit of natural language deduction in our sessions. So we'll get there. It is not difficult to enrich, to enhance the rules of syntactic structures, the rules that are presented in syntactic structures. We can add A1 very easily. We could have said sentence goes to sentence plus L plus sentence. Now I try to write what it could mean. So we have seen that sentence goes to NP VP. That rule is already there. But we can say also there is another route, there is another option. A sentence also could be split this way. It could give you another sentence, and an L will tell you what L is, and an other sentence. So thus one sentence is split into three parts. Two of them are sentences, and there is an L, and we interpret L as, so we can now say that L goes to either and or if then, anything. Suppose we choose and this sentence, we can rewrite this sentence as anything, John walks or something like that, NP VP. Now notice that right now we don't have any rule that allows us to write John walks or Tom walks. It is not difficult to introduce such a rule, but because our rules, if we remember, in our rules we have seen that a verb goes to a VP goes to verb and NP. So basically we have rules for transitive verbs that have objects. We don't have a rule for intransitive verbs like sleeps or walks, but we can have those rules. How? We could add a rule like VP goes to verb plus NP or verb. This was a possibility. Or also we could have done it this way. Actually this is not a very great way of doing it, so I suggest that we could have done it this way. We could have said that VP goes to VP singular like NP singular and VP plural. And then we could have said that VP singular goes to just verb and VP plural goes to verb plus NP. Now we can easily see, sorry, we shouldn't write singular plural. Once again, sorry, we actually are talking about transitive, intransitive. So this is actually intransitive. VP intransitive and VP transitive, because transitive verbs will have objects, which is the NP. So this is already there. So a structure like the man hits the ball could come under this rule, where hits the ball is this type. There is a transitive verb, and the man sleeps or the ball sleeps or anything like that would be, it's nonsensical to say the ball sleeps, but syntax will be indifferent to such a nonsensical sentence. It is semantically nonsensical, but it makes perfect syntactic sense to say that the ball sleeps. We could have easily said that. That's a grammatical string. So then we could have added these rules instead of having instead of having, for example, this rule number 2. So then we could derive both the man walks and the man hits the ball. Anyways, so let us assume that we have added those rules, and now we can make a sentence like we can make a sentence like John walks. John is not there in our list, so we can change it to the man walks, or the man sleeps. We need to add sleep then to our list and all that stuff. So we can see that with a few additional rules we now can enhance the Chomsky grammar sigma f, the original Chomsky grammar, and we can come up with something like sigma prime f prime, which is enhanced sigma f, which is sort of slightly modified, slightly strengthened sigma f. So by using this grammar, this modified grammar sigma prime f prime, we can now make sentences like the man hits the ball hits the man walks. These sentences could already be made in the old system. The third one, it was not possible for us to make the third sentence, but with additional rules we could. Now we shall consider an argument in ordinary English, and we will try to see whether the argument form is all right. The argument is given here. So it is precisely this: if the man hits the ball hits the man. the man walks and hits the ball, therefore the ball hits the man. What to do with this? This is a very simple argument. We can see whether it is valid or not. We'll talk about validity in the next session, but there could be a very complex argument. We need to have some device, some formal device to evaluate an argument. We'll do that in the next session. Thank you.